Okay, so we're going to start talking about SQL queries, and we're going to go through some examples. Now, as we mentioned previously, SQL stands for Structured Query Language, and it is a query language for structured databases, specifically relational databases. Now, this is a very standard common language that is basically used on all relational databases. So relational databases are the most common database type still out there. It is the oldest database type. And if you know how to use SQL, you are very employable in the sense of lots of places use SQL databases. And so you can move from MySQL, the SQL Server, to various other kinds of SQL databases. And it's more or less 90% of it is identical. So once you get good at it, you can move around. You're not committed to, I learned MongoDB and now you want me to do what? Which is completely different. So this is one of the differences between SQL versus NoSQL databases. There's so many different types of NoSQL databases, and they all kind of have their own proprietary language to work with them. SQL databases, relational databases, they all use SQL. Now, it is worth kind of mentioning that a lot of these different databases, they will have what sometimes gets referred to as SQL Plus on top of it, where, again, 90% of the language is identical across all databases of this type. But then SQL Server decides, well, I'm going to add a couple more bits of functionality that we think our customers would benefit from. And then MySQL, well, they'll implement those maybe slightly differently in a different way, or they'll not do all of those, but they'll do something slightly different. And so there's usually a few things that are particular to different databases, but they're not the kinds of things that you do on an everyday regular basis. They're kind of specialized functions for those databases. So it's worth being aware that there are minor differences from implementation to implementation, but broadly speaking, you can copy one SQL query from one database into another database system by a different company, and most of the time it will work just fine. Now, there are some key uses for using SQL. Now, for the most part, we are basically going to be querying databases, extracting data from the database, because as data analysts, we're not usually the ones creating the databases. We're just getting data out of it. But you could go into the management side, and then you would have to potentially do the creation tools as well. But we're going to focus mostly on data retrieval. We are going to look at some of the other ones, but that's going to be our main focus, particularly today. But there's also data manipulation, so inserting, updating, and deleting records. And so if you're working with data all the time, you may do this on a regular basis if your job is to enter data into the database and make sure that it is consistent. So, you know, the receptionist or the data manager at the hospital, for example, they have to know how to enter all of this stuff. They don't necessarily do it with SQL because there's a form that someone has set up for them. But in the background, they're using these commands. Data definition. So this is creating and modifying database schema. So this is the database designer that tends to use these. And then data control is managing access and permissions to the data. So there are subsections of SQL. And typically, depending on your role, you may use these 3, or may use only these 1, or you may use a form that accesses another one that you don't really know that you're doing, but that's what you're doing. So, but there are different subsets that have these different roles, these different tasks. All right, so we want to talk about the basic query structure, because that's mostly what we're going to be doing, is querying the database. And we're going to do an example database and do some queries on it at some point. Now, the main query that we're going to use is called select. And so this is anytime you start a query in SQL, it's going to start with select. Then you're going to indicate the information that you want to retrieve from a particular table. So from tells it what table to go look for to retrieve this information. Where typically is a filter function. So we have filters in pandas. We've seen those before, but this will sort of limit the kind of information that you're getting, age greater than 60 or something like that, or whatever. Order by sorts the results, either ascending or descending order. So if you want like the top 5 salespeople for the month, you can have them ordered highest to lowest, or maybe the lowest 5 because you're thinking about firing them. You can do it the other way. And then there is a limit or some other kind of function at the end that will limit the number of rows or skip a specific number of rows so that you can manage your results. So this is like the head function or the tail function, for example, in pandas. We can also specify, if we do like a slice of the data, specify like which rows we want it to report back. But limit 10, for example, would be an example of where we just want like the top 10 rows. It's like the head of the data. So we don't really need all the data, but we want to see what it looks like so we can figure out what other kind of queries we want to do on it. So basic data retrieval queries are going to look like, so very, very simple ones to start with. So again, select statement starts our query, and then we would list the column names that we want to retrieve from the table. Typically, we just put a comma in between them. And then you'll often see this with SQL queries, although it's not strictly required. But every time you have one of these major commands, you will switch to a new line. But you can just string it across in one line. It doesn't change the way that they do it, but it's usually easier to read if you do it this way. The command statements, again, they don't have to be this way, but it's a very common SQL practice to capitalize all the function names and lowercase everything else. So select is all in capitals because it's a SQL command, and then the column names are in lowercase because that's information from the table. And then from is a SQL command, so it's capitalized again. And then the name of the table that you're extracting this information from is in lowercase again, although you do have to match the case of the table. So if the table has capital letters naming it, or the column names have capital letters in them, you do have to include those. And then the SQL command ends with a semicolon. So just like C, don't forget that because it won't work if you leave off the semicolon. If I want to retrieve all the columns from a table, which is extremely common, I replace the column names with an asterisk. So select star from employees will pull the entire employees table, all of the columns. Whereas if I specify the column names, then it will only pull those columns. So often what happens is if you don't know, you pull a bunch and you limit it so you can see the head, and then you can decide, okay, which columns do I really want? And then you redo it without the star, but with the specified column names, and then you leave off the limit. So filtering with where. So typically you do this with equality, inequality, or other comparison operators. And you can use conjunctions and other things in order to make it a little bit more sophisticated. So here we're pulling employees' first and last name from the employee table, and we're specifying a particular department. So we're pulling from the sales department. This is a text string, so you put quotes around it. And we also are doing a second filter where their salary is greater than 50,000.
I don't understand why sales is implications.
Because it's a text string. And so it's an entry in the table that is text. And so you can't just write equals sales without the quotes. It won't understand it.
But salary isn't, I mean.
Salary is a field name, like the department.
Oh, okay. Okay.
But you don't put quotes around numbers. Only text. So it's like Python in that sense.
And all numbers are seen as numbers, and it doesn't ever, like Python, you can't have a number that's a string, but
I think it depends on the way the field is formatted. But if it was formatted as a string, you would have to put quotes around it. So if you had a department that was named 2020 or something like that, because the rest of the department names are not numbers, they're strings, you would have to put quotes around that because it would read it as a string. I would not recommend doing that if you're setting up a database.
Yeah.
Because that would be confusing in the long run. But normally, any text fields would need quotes, and then numerical fields don't. So this will filter both on the department and then only put out the people in that department whose salary is greater than 50,000. And we use the and to say that both of them have to be true. And you could do things like or as well. So anyone from the whole company that had salary greater than 50,000 and also everybody in the sales department would be the or, and it would return both. You can also do, instead of inequalities, you can also use things like in if you have a list of categories. So department could be in, and then you would have a list of maybe 3 departments that you want to select. So you don't have to do separate conjunctions like this or this or this. You would just put it in a list and have it in. Between, so if you want to filter within a range, so again, you don't have to do and or. You could do salary instead of less than or greater than 50,000 and also less than 100,000. You could just say in between 50 and 100,000. Like you could use on text strings for pattern matching. So for things like looking for, I don't really know what the guy's name is, but I know that it starts WOL. And so then we'll pull out all the WOL names from the database.
so the ones that are in.
So like is it CZ at the end or SZ or SCH or those Eastern European names, has it been anglicized or not anglicized, and who the hell knows? So you just pull out everybody with a certain pattern, and then you can do that. And then, so here's some specific examples. So in the in version, we have it department in, and then we put a list in parentheses of the names of the departments that we want. Again, each department name is in quotes because it's a string. Employees where salary is between 40,000 and 60,000. And between always goes with and. It's not between or. It doesn't make any sense. And then here we have like. So this is a case where we want a name to start with J and then other stuff afterwards. And so there are different ways of doing this. So you can indicate like the number of spaces afterwards, or just anything that starts with this letter of any length. And then aggregation and grouping is done typically with these common, like our really basic statistical functions that we've done them in Python. So count, sum, average, min, max, things like that. Not regression or anything like that. But I can get the count of the number of employees. And then I can, in my table, I can specify how I want it to output, and I can give it a label. So select, I'm counting all the observations from my employees table, and I'm going to output it as a column with the name total employees. Otherwise, it will actually just give you back the formula. It'll give you back count star, which is not necessarily very meaningful. So again, average salary. This will calculate the average salary, and then if you don't specify an as operator, then it will put it as just the top of the table. It will just say average salary in the original version, AVGSALRY. But you can specify something that's more meaningful to the output, especially if you're planning on doing additional operations on it. You don't want these weird formulas. And then you can also do combinations of things. So separated by commas. So I want the minimum salary and I'm going to output it as the lowest salary. And then also from the same table, maximum salary, and then output it in another column as highest salary. And then of course we could add some additional things like filtering or grouping or whatever, but the group by clause groups things together. So if we want to find the count of employees by department, then we're going to select the department column, and then we're going to count how many employees there are in the whole table that are in that department, output that as the number of employees column. So we'll get department name, number of employees, but we're grouping by department. So what this will do is it'll only give us one output for each department, rather than every time there's a department, it will spit out the same count over and over again. And so again, we can select department name and the average salary, and it'll give us a table by department, average salary. It'll group by department. And again, we're having is another way of filtering the data. Again, average salary greater than 50,000. Having is typically used with filtering based on aggregated conditions, and not, so we're not filtering first and then grouping. We're grouping first and then filtering. So we use having instead of where. We can join tables. So there are actually 5 kinds of joins. Only 4 of them are listed here, which is disappointing to me. But there's an inner join. Now the inner join returns rows that have matching values in both tables. There's a left join, which is sometimes referred to as a left outer join, which preserves everything in the left table and then pulls in anything from the right table that matches. But if there's nothing that matches, it leaves nulls.
So is this the same as it is in Tableau?
Yeah. And pandas, and yeah. It's all the same terminology. Right joins, they keep everything in the right table and they pull in things from the left table that match the right table. But if there's something missing, it leaves nulls, leaves blanks. And then the full outer join keeps everything in both tables, but it could have nulls in either thing. Now, if your database is well designed and it's all based on actual collected data, it is entirely possible for all of these joins to produce exactly the same results. It's only going to be different if, like, you have all your data, for example, maybe you had collected all of your data for the last 40 years when there was only 2 genders allowed. And now all of a sudden you have an X. So you've made room for an X in your database, but you don't actually have anybody that has taken the label X. So then if you did a right join versus a left join, you would get slightly different results because the X would be preserved, but it wouldn't go anywhere. It wouldn't match to any customers. But typically, most of these will give you the same results unless you have a situation where you have structures in your database that are accounting for things that you don't actually have observations of. So like you don't have customers from every state, for example, another sort of more general thing. So there's just some example text to work from. So an inner join example. So normally you have to specify the table that the column is coming from. So here we're pulling the first name from the employees table, the last name from the employees table, and then we're pulling the department name from the departments table, and we're going to join employees to departments. And then what column matches? Well, it's going to be the department ID. It's a foreign key in the employees table. It's a primary key in the departments table. But that's how we know what employee is employed by which department. And then we just change inner join to left join or right join or whatever, depending on what we're doing. The left and the right just depend on which one you list first is the left one. The one we list second is the right one. And in we'll see when we actually do SQLite and we play around with this in Python. You can't actually do right joins in SQLite because it's a stripped down version. So the way you would do that is you would just flip the order of the table and make the one that goes on the right, make it the left one, and then the left join will do the same operation. It'll just, the columns will be in different orders. Now you can also do a natural join. And a natural join is going to look at the two tables and identify columns they have in common and then join on those. So you don't have to specify which columns are which. And also you will see examples in various places where they will rename the tables as something that's shorter, A and B or something like that, just so they don't have to keep writing out the table name in front of all of the field names. So if we treat employees like table A, they'll write A dot first name instead of employees dot first. And then the cross join is the fifth one. So I'm not surprised it's here because this one is fun, even though we like almost never use it. It's very mathy. The cross join returns the Cartesian product of two tables, which is to say that every entry in the left table gets matched with every possible entry in the right table. And so the size of the table is the product of the entries in the first table times the product of the entries in the second table.
You said we're not going to really use
this. This doesn't happen very much. I mean, you can, again, it's something that you can imagine. There are certain circumstances where you might want to do that. But they're very uncommon. But it's, again, it's worth knowing that it exists. And so this also gives us an example of we're specifying a name, a renaming for the tables that we're pulling from. So, and again, this is an example of where you might want to do a cross join because you want all of your stores to have all of your products. And so you could have a list of every store with every possible product. So if you have a lot of those, it would be a very long list because you'd multiply the number of stores by the number of products, and that would get you but at least then you would be able to create, let's say, an inventory of how many products are in each store. But so after the name of the table, just put what you want to call it. So here, products A is an indication that we're going to rename products in our query as A. So I don't have to rewrite products all the time. And I'm going to call table stores B. So when I refer to product name and store name, I don't have to rewrite products.product name and stores.store name. I can just write A.product name and B.store. Yeah, it's just a typing saver thing. For a query this short, it's probably not that big a deal, but when you have a lot of columns that you're trying to pull in, this can really reduce the amount of typing and the potential for errors. Because did you put 3 E's in employees? I don't know, maybe. Because you only had to type it 5 times, right? Now we can make our queries more sophisticated by doing subqueries and nested queries. So in a select statement, we can do a subquery to calculate a value within a larger query. So again, some examples. So here we're selecting first name, last name, and within that, this is essentially saying like where we're getting the query from. We're going to select the department name from the departments table where employees and department ID equals departments.department ID as, and then we're outputting it as department name. So this whole section from this parentheses here, not all the as, just there, that is all a subquery. And then the output is just going to go into our table, but we don't want the name of the column in our new output table to just be select department name from departments where employees, blah, 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 blah. We just want it to say department. Yeah. And then these columns are coming from employees. So that's a subquery within a select statement. We can also have subqueries in a where statement. And again, the structure is basically where you put it where you want it, but then you put it in parentheses. So here we're going to select employee first name and last name from employees, but our where statement, our filter, is we want to select employees whose average salary is higher. But we first have to calculate the average salary. So our subquery is calculating the average salary overall, and then that number is going into the where statement, and then it's only pulling employees whose salaries are above average. But we don't know what that is to hard code it in advance. So, and then there's some examples of when you might need to go through some of these more advanced things. Again, we're not going to go too far into this because these subquery things can be crazy. But particularly when you're doing, when you combine them with joins and things like that, I've seen some queries that are like 15 lines long just because there's like 2 embedded subqueries. And my inclination usually is just to pull more than I need and then fix it in pandas. But but then again, I don't work with SQL on a daily basis, so I haven't had a need to get better at the subqueries. It's easier just to do it in pandas. And I'm all about efficiency for me.
Right. And I mean, you're filtering it somewhere.
Right.
So it doesn't really matter where.
Right. But in particularly people that work with databases all the time, or if you have a particularly large amount of data that you're managing, like I would imagine that multiple subqueries would be essential if you're trying to pull Amazon customer data, just because Amazon customer data is just so large. You don't want to pull all the data that a bunch of it you're not going to use. You would really want to make sure that you're just pulling the data that you need because it's already going to be kind of unmanageable.
Right. You would want my order number, not every order I've ever made.
Right. Right. So in particular, so in your coffee shop example from earlier, you don't really care about all the subqueries. You can clean it up later. But when you're dealing with millions, hundreds of millions of customers, you don't want to pull 100 million customers or even half of that or a quarter of that. You really want to make sure that you're only pulling the data you absolutely have to have, because it's going to be unwieldy probably almost all the time anyway. And you know, your spreadsheet can only handle 1 million rows if you push it. So you want to make sure that you get all those subqueries in there so that you're really only getting exactly what you need and not filtering it later. But again, if you're working with databases that big, then you will do this a lot and you will get much better at it just out of necessity. All right, so we talked about joins in SQL. So now we're going to talk about doing joins, joining tables in data analysis, because we don't always have all the data that we want in one particular data source. And so there are often circumstances where we want to reuse data from other sources. We want to expand the data that we have available. And so we need to put the data together into one thing. And the joins are going to work more or less the same way. We're just going to be doing it in pandas in a slightly different way. We are going to see examples of doing SQL joins in Python using actual SQL code, but you can also do all of this just with pandas. So when we do a join, generally, of course, we're joining two or more potentially tables together on a related column. Particularly when you're doing data analysis, even if you're pulling it just from a database, sometimes you have to combine 3 or more tables in order to get the relationship that you're looking for. So one of the databases that we're going to look at is a school scheduling database. So imagine that you're trying to figure out like what professors has a particular student had. Well, there's no connection between the student and the professor directly. So you would have to figure out what courses they took, and then which professors taught those sections of the courses. And then you would be able to make the connection between which students had which professors, or vice versa, obviously. So joining more than 2 tables is certainly something that can frequently come up, depending on how sort of attenuated the relationship is that you're trying to do. Our examples are often built on just 2 tables, but typically, like even in SQL, you do the first 2 and then you just string the 3rd one on the end, because it'll treat the combination of the first 2 joins as a table, and then collectively you will just join it to the 3rd one. So you just string like inner join table until you've exhausted your list of tables. Okay. So why would you do this? So we want to integrate data from different sources. We want to enrich the data that we have. Again, maybe we have information on the weather on a particular day that we collected data that might have some impact on something that we were measuring on that day. Maybe the electrical nodes on our instrument are affected by the humidity. Who knows? So you want to pull in data. Maybe you want to pull in customer demographics or product details or information about the community in which the customer purchased the product. And when you're handling normalized data within a relational database, everything is divided into multiple tables to reduce redundancy. So in order to just get back, like, what is all the data for one particular customer transaction, you have to pull data in from multiple tables and kind of put it back together in an unnormalized form. So one example that we have here is like employee performance. You want to find out like if they're sales staff, like how much have they sold, what kind of products are they selling, how many transactions of sales are they doing, how much is each transaction worth. Maybe they don't sell that much, but they sell a lot of high dollar products, so you wouldn't want to compare them directly to the guy that manages the candy counter. So, or this furniture might have a different number of sales than the shoe department. So you want to make sure that you're comparing like to like. But you have to pull all of that information in from multiple tables in order to make those assessments. You would need the department that they're working in and the sales data and the employee data. So that's at least 3 tables. So again, we've talked about some of these. So I'm not going to go through all of them in the same level of detail again, but these are some additional examples that you can use as you go through. So here's our inner join. A natural join, which you can also use to replace inner with, would allow you to skip the ID identification that you're matching with, but it will act as an inner join. So if you had all of this here like this, but then you just said natural join on customers, and then you skipped the whole on blah, 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 the natural join will look for the 2 columns in the 2 tables that agree. Now, sometimes in poorly designed databases, the matching columns won't have the same names. And then you have to specify, and you can't use natural join. But when you use natural join, assuming the tables are the name the same in both tables, which is very common in a relational database, then you don't have to list the on blah, 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 because that is redundant information. But occasionally you will have, especially if you're pulling data from external sources in Python or whatever, the column names may not be the same, and then you will have to be very specific. What is the column name in one table? What is the column name in the other table? And again, here's our left outer join. And we talked about that before. The right join, again, in typical databases, you have both the left, right, and full join. But in SQLite, we actually only have the left join. At some point, I will show you an example of how to get around that explicitly, because we're going to be doing the practice in SQLite and not in a full database, but the structure is identical. So another example where we might want to do this would be combining user data with website activity logs. So, for example, I see this in my student profiles all the time. When was the last time my student logged in, and how many hours did they spend on the platform? And maybe there's a reason why he hasn't turned in any assignments, because he hasn't logged in 2 weeks, and that kind of thing. We can also do data aggregation, of course, and we've seen examples of this already when we were doing imputations. That mean method that we attach to our imputation analysis, that is an aggregation function. We're calculating the mean on the data, just that in that particular context, we were then replacing it with a particular missing value. But you can just do these calculations independently. You don't have to use them in some additional calculation. We can build these tables of summaries. So we want to do statistical summaries. We can do columns of all of the different variables, and then statistical summaries, values for each of the min, Q1, median, mean, standard deviation, Q3, maximum, whatever. We can throw it all in one table, and those are all aggregation functions. And particularly when we have large data sets that are very difficult to work with, or when we want to, for privacy purposes, we don't want to give out individual information, then we can aggregate the data so that we can give out some information, but not have to worry about risking individual personal information. So we might aggregate it over like a month to say like what's happening in a month. There's a data set on sunspots that goes back to like the 1800s or something, but it's a monthly sunspot average because it has decimals in it. It's not a day-to-day one, because you can't do it every day because there's clouds and stuff like that. But people have been counting the number of sunspots on the sun for a very, very long time. But you have to aggregate it over a month. Otherwise, you have an irregular time series and it's impossible to work with. Or you can do, again, something like that in a community where, like in a census block, you would report an average salary or an average home price or something like that, so that you're not reporting like this particular family has $450,000 list price. This person over here, it's not quite so good. Yeah, so too much personal information. So aggregation will preserve individual personal privacy. And again, this is very common when we're doing reports for an employer, monthly revenue reports, monthly sales reports for the sales staff, customer segmentation, operational efficiency, when your production data and things like that. All of these involve aggregating lots of data, converting it into a single number. So again, these are some examples of doing this in SQL. We already talked about those. Once you have the aggregated data, Now this is sort of more data analysis portion again. So then you can do things like do visualization. So you can take your summarized data, your aggregated data, and make bar charts or pie charts or line graphs. Now, and again, some of this we did, when we were doing the graphs, we were aggregating the data in pandas usually, and then making our graphs of them. But again, you can do this directly in SQL, or you can do this in Python. And then once you have your aggregated data, you don't want to make a pie chart of individual observations. That doesn't make any sense. Excel will not do that. You have to aggregate and summarize the data before you can do some of these graphs.
So is it like Excel where, you know, it can do some stuff, but it's not as powerful as using pandas?
Well, I think Python will probably try to make a pie chart of, like, if you have 100 observations with individual numbers, it will just make a pie chart that has 100 slices that are completely unreadable. Whereas Excel will just not
Well,
do
so
anything.
no.
It'll just give you a
I'm not
blank.
doing it.
Yeah. Like, here's my legend with all the labels, but there's nothing in the graph. So one way or another, you will either get garbage or it won't do anything at all. So it should be a reminder that you have to summarize it first, but you would think that, but it doesn't actually work in practice. I've seen way too many people just like send me broken graphs or things with 100 pie slices and think like, that's what I was aiming for. Okay, so I think this is a good place to take a break. So I included at the end of this section resources both for working with SQL and Python for various different means. We're going to look at SQLite in the lecture. If not today, then next week. Definitely lots next week. And I also included a link to doing some of the merging, the joining commands, but in pandas, not in SQL, because we have lots of examples of SQL. And the SQL links are above in the bottom of the first section. So you'll have access to links for both directly in SQL and also directly in sort of standard packages in Python. So this is a good place to take a break before we switch over to Python. So I'm going to pause. All right, we're going to pick up where we left off with our Python. So we're going to look at a couple of different things today. We're going to talk a little bit about rescaling and some SQL stuff, and there's just a bunch of little things in here. So obviously first thing is first, we load pandas, which takes forever. And while that's loading, just remind people for what we're going to do today and next week, you're going to need to install SQLite 3. And you can do it in Jupyter, but then it may not run. You might have to close it out and restart the kernel. It's easier to do it from the Anaconda prompt. Normally other packages installed fine using pip, but for some reason I can never get pip to work with SQLite 3. So you can use the other installation command, which is conda install. And then that seems to work better. But you will need it in order to get things to work. So we're going to first install the practice data set that we've been using for some of our examples. And I also have a new one that we're going to look at this week that has some more null values in it. Health data nulls. I have two versions of this data set. That's why it says nulls on the end. So I'm going to load both of these. And I believe I put both of the files in the week 7 files zip. So you should have them. So again, this first one is just the data we've been working with. And then the health data, you can see there are some NANs in here. There is some missing data. Now, just for context, to kind of explain what's going on with this data set. The blood pressure variable is the variable that they want to predict. And every observation has a blood pressure variable, a value. The blood pressure has been renormalized to percentiles because blood pressure is complicated. It has a top number and a bottom number and blah, 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 blah. And so they just aggregated it all and just called it a percentile value. So the values in this column are between theoretically 0 and 100. And so they're not your typical blood pressure values that you might be expecting, but that's what they represent, their percentiles. And then these other columns represent the income is sort of what you'd expect is just a number. The age, again, it's importing as a float for some reason, but it's an age like we would normally do age. Alcohol, I'm not exactly sure what they're measuring. It could be ounces per month or something like that. Exercise, I believe, is minutes per week, or something to that effect. And then smoking, I think, is the number of cigarettes smoked in a particular time frame. So you have some people who don't smoke a lot but do occasionally, and then you have some people who are like more heavy smokers. Exercise has a lot of zeros. All right, so we're going to drop the person column from both of these data sets because it's not a variable, and so we don't want to analyze it because it's just the index, basically. So this will drop both of them at the same time. And then we look at the data again just to verify that, yes, the person column is gone. Now, we've talked about different ways of handling different kinds of values. Sometimes we have to prepare data for a particular model, which we'll talk about at some point. But also just to handle outliers, you might want to rescale, or depending on the kind of model that you're doing, if you're doing any kind of distance calculation, or if you're doing penalized regression or something like that, you often need to rescale because when you're building a model that's not linear, in particular, with columns that have values that are as distinct as salary and like the number of cigarettes you've smoked, that's like a huge discrepancy. And so in a traditional linear model, the coefficient will just do the scaling and it's not a big deal. But if you're doing a distance metric, the income at this scale will completely overwhelm all of the other variables. Even if it's otherwise well behaved, it's just so much bigger than all the other values in the data set that it may make certain models not work as well as they otherwise would. So we have different scaling functions we can apply to clean our data. So in the sklearn package of scikit-learn, there's a lot of pre-built scalars. At some point, we're going to look at doing this manually, but for right now, we're just going to look at the built-in function. The standard scalar basically is going to calculate the mean and the standard deviation, and then convert our values to a z-score. And we can apply the standard scalar to specific columns, or we can apply them to the entire data set. It will not work on categorical variables, though. So here in this example, I've specified from our practice data set just the two columns that are numerical. And then rather than replace the columns, I've tacked on new columns so that I have both the original unscaled and the new scaled versions. So salary, rescaled, again, these are now some positive and some negative values because they represent where they are in the normal distribution. And then also amount spent is now roughly in that -3 to 3 range. And probably mostly in the -2 to 2 range, because that's where you'd expect 95% of your data to be. You can also sometimes bin your data. So sometimes you will have data that like maybe income, it's got lots of numerical values, but maybe you want to compare it to another data set that doesn't have numerical variables. Because, you know, when you ask people survey questions, they don't necessarily want to tell you exactly what their salary is. Or like in our one data set, we have age groups, young, middle, and elderly or whatever. And maybe we want to do some comparison so we can bin our numerical data. If we want to make certain kinds of graphs, maybe we want to break out a box plot by decade or by generation and another variable. We would need to bin the data and make it a category. And so this is an example of taking the age data in our health data table and converting them or adding on our age group data. So in this example, this is going by 2 decades at a time. So we can think of these kind of like generations. A generation is roughly 20 to 22 years or whatever. So 81 to 100 would be like the silent generation, Joe Biden's generation. And then 61 to 80 would be just a few years younger, the boomers. And then 41 to 60 would be my peeps that everybody forgets exist. I can't tell you how many times I've seen lists of generations that just completely skip over X, like we're not even there.
Invisible generation.
21 to 40, again, roughly the millennials, again, not exactly, but roughly. And then I guess Z or alpha or whatever. I guess alpha would probably be like under 5s now, but so this is mostly Z, but whatever. So we're binning the data. And so now we have the original age values, but now we have an age group. So again, we could think of it as sort of a generational thing. So if we wanted to analyze, like maybe the younger generation is doing a better job exercising and smoking less,
yeah.
and the older generation is drinking more and smoking a lot. And we could look at it as a group rather than as individual numbers, like in a scatter plot. We can also, again, we talked about if your data is very skewed and you have a bunch of outliers, you can do log transformations to help manage your data. So here we're pulling in NumPy, which is a numerical Python package, and we're going to calculate the log of our values. Again, don't do this if you have negative values because it will yell at you. But again, if your data is particularly skewed, and income sometimes is, then this would be a way of having really big incomes not be quite so far away from the rest of the data. Like if Bill Gates were here with us now.
If we keep Michael Jordan.
Yes, Michael Jordan or you know, the scourge of the current American government. Although his income is falling fast. We can also create new variables. So if we want interaction terms, maybe we want to create a model based on the ratio of 2 of our variables. Maybe your salary over income, or what percentage of your income are you spending in the store. You can do mathematical operations on your columns to engineer new features for your data set. So when you are creating names for your tables, think about what you want to name the columns. Sometimes it's useful to be very explicit, and sometimes that's just way too damn long to kind of have to retype constantly as you're doing your models. And spaces are not always convenient, but it's a choice. So our example has lots of spaces and is very, very long, but it's very descriptive and you know exactly where it came from. You could also just call it something simple and put that information in a data dictionary somewhere.
Those spaces aren't going to cause a problem somewhere down the line.
Well, so there are shortcut ways to do Python where you just do a dot in the column name, and you can't do that with these. But most of the time you do Python, you do it with like the brackets and the quotes around it, and then the spaces don't matter.
Okay.
So there's always a way to do things even with the spaces there, but you don't get to do some of the shortcuts without lots of extra stuff. And then when we are looking at categorical data, if we want to put them into certain kinds of models, we have to recode them as numerical values. So we talked about one-hot encoding. And so this is the get dummies function is going to convert all of our categorical variables into 0 or 1 columns. Now, in this particular data set, gender and home have only 2 values, so we'll only get 2 columns out of it. If we were to do like the age column, we would get 2 new columns out of it because there's 3 categories in that column. So it's always 1 less than the total number of categories, because if you're not middle-aged and you're not elderly, then you must be young, just by default. And if you're not a man, then you must be a woman. And if you're not a homeowner, then you must be a renter. There's only 2 observations, 2 values. Now, if you don't use the drop first equals true, it will keep both columns, and then that information is redundant. It'll create 1 column for every category. But that's, you can't use them all. That's linearly non-independent. So drop first equals true will get rid of 1 of them. The problem with this particular drop first equals true is that it will drop the alphabetically first thing. So maybe that doesn't matter if there's only 2 categories. But for like age, it would keep middle and older, and it would drop young. No, I take that back. It would keep older and young, and it would drop middle, because middle is alphabetically first. In the gender, of course, it drops female because male is alphabetically later. But if you do this for days of the week, it will drop Monday. No, it'll drop Friday. That's what it will drop. And then it will keep everything else after that. So 0, 0, 0, 0, 0 would be Friday. So everything you're doing, you're comparing to what would happen on Friday, which is weird. So sometimes it's better to not use drop first equals true and then manually remove the column that you want to treat as the default. So the same way we drop the person column, you would drop, maybe Monday is the right day to be the comparison. You would manually come back in and just drop that. But that's what this function is doing. It is dropping the alphabetically first one, whatever that is, whether it makes sense or not. And it's not dropping the first one it comes to in the list. It's alphabetically first.
Amount spent.
Yeah. Now, sometimes data will get imported into pandas incorrectly. So something that's supposed to be a number will get imported as an object for some reason. This function will make sure that you can try to coerce any data in your data set into a number. Now, if there's an error, because it can't readily be converted, we do have a coerce option. If you do that, you should make sure that you check to see what the coercion did. Usually you only do this when you know there's an issue, and so you know what to check. Sometimes this will just drop things like $signs or commas or whatever. But sometimes it will do strange things because you're forcing it to do something it doesn't really want to do. So you should always check the results. Now, in this particular case, the salary imported properly, so this function did absolutely nothing. But that's fine. Now, if we want to identify any missing values in our data set, there is a function called isNull. And then the .sum will calculate the number of null values in each column of our data. And it will give us a nice list. So we can see that blood pressure has no missing values. So that's Again, that's the one we're trying to predict. And then we added age group, so that appears here twice, but all of the other ones, there is some missing values in all of those individual data sets. There is a 1,000 observations in this data set. So if there were only nulls in one column, this probably would be something we could at least contemplate dropping. But when you add all of these up, even if you ignore the double count of age, you get well over 300, like 360 or something like that, which is above the 30% threshold. So this would be a case where you would not want to just drop the values because they would create too much bias. And if you look through this data set, you'll see that every observation is only missing one value at a time. So it's not like the MBA data set where there was three rows that were missing like 5 values each. This is like all over the place. So it ends up causing you to delete more data because there's only one observation missing in each row. So this is kind of a classic example where you would definitely want to do some sort of imputation here. Now we can look at what happens when we fill the data in with the mean. So when you do this, again, you generally want to try to create another column and then preserve the original variable because you want to know where the missing values were. And then, but then when you build your models, you can build them on the column that has all the imputations. The median, I pulled in a few, 10 rows so we can see what happened. So the first age imputation doesn't occur until row 7, so it didn't show up in our look at the first 5 rows, but you can see where the age as the mean looks weird because we don't report ages as 44.8 most of the time, unless you're going by the days, like, the youngest Olympian, they care about the months and days, but normally we don't. Whereas if you do the median, the most that you can expect is that it'll be a 0.5. So I have been known to run around telling people I am so-and-so and a half because I'm weird like that. My dad sold insurance, and so I was counted as the next age up when I got to the half. And so I would try to persuade him that the insurance company thinks I'm old enough. Why can't I do this 6 months early? It never worked. But I did try. All right, and then mode imputation. Now, one of the issues with the mode is that it doesn't always work. And sometimes it will give you sometimes inconsistent results. But I've included it here just kind of as a reminder. Sometimes there are multiple modes, and sometimes there's no mode at all. So if there's no mode at all, every value has exactly the same number of observations, you may get an NA no matter what you do, because everything is the same. If you have multiple modes, you can specify which one in the list you want by adding that index entry afterwards. But then it will give you the lowest value. It won't give, because often it's numerical order when it goes into this list, and so it won't give you the larger value. So this is not always ideal, but think about our exercise variable in this blood pressure data set. The missing data, I don't think it's crazy to think that like they're not reporting the fact that they don't exercise at all. And the most common value in the data set by far is no exercise. So a mode would make sense here. Of course, there's only one value that's the mode in that particular variable. But it is something that you sometimes do have to worry about. It won't work all the time. And it will sometimes, again, if there's multiple modes, you may not want the lowest one. But mode imputation, again, it will fill in this age one doesn't like give me enough to see where the age was. but it will give you a value that exists, an actual age. So it'll look like the rest of the data. But you might have an average and then just accidentally have a lot of 33-year-olds, which won't look very similar to the 45 average. So again, use it with care. But there are times where it's important. Another way that you can impute things is with some kind of regression model. And we'll see more about the regression when we do modeling, but I've included it here as an option for imputation. This is a KNN imputer. So this is basically doing a regression using KNN. So it's calculating a certain number of neighbors, and then it's averaging all their values together, and then it's giving that as the value for the missing thing. And you can do multiple columns at the same time, which is nice. So normally when you're doing a mean, you only can do one column at a time, but this will actually calculate the imputations for all of the missing columns if you want to. So it does take a little longer to run. But now I have a lot of more columns on my data, but it filled in all of the NANs. So for instance, exercise, it filled in 36.2. Now again, one thought is that maybe they're not reporting the data because they're not exercising, but this is suggesting that there are people that are similar to this person in the data set, and that the average of those observations is actually that they do exercise 36 minutes a week or a day or whatever. So all of these imputation methods are not going to give you the same value. They're going to give you different values. And so at some point we will want to analyze the outcomes to see how does that affect the outcome. Does it skew the standard deviation significantly? Does it do something unpredictable? So that will be an analysis that we'll have to do. And then we also have this essentially multiple linear regression. I've referred to it as MRG because it's multiple regression. But this is an iterative imputer. And again, we get, this one will do, the ones in the scikit-learn, they can do all of the columns at the same time. You don't have to do one. It'll iterate through all of those. Now, in this case, the multiple regression imputer, that same missing value for exercise, they gave us 36 in the previous KNN analysis, gave us 50.5 in this one. So it thinks it exercises more. Again, I don't know off the top of my head which is more or less likely to be true, but the different results are something that we would need to consider in terms of, are we extrapolating too far out of the range of the data, or does this make sense? Now we can use the describe function to calculate some summary statistics so that we can compare what the outcome of our different imputation strategies are. So we're just going to look at the age column here. So for example, the original column had 896 observations. The others, the imputed ones, have all filled in 1,000 of them. We have a minimum of 25 and a maximum of 65. That seems to still be the case everywhere in our data, so that's good. What about our standard deviations? One of the potential issues with imputing, if you impute the mean or the median, you're not going to affect the mean or the median very much, but it's the variability that could be affected. So in the original data, it's 11.9. In the imputed columns, it's gone up to, or gone down to 11.2 in some of these, 11.8 in one. The median, this one doesn't seem to have affected it that much, but it's a little lower, 11.4 in the KNN, or the mode column. actually, or one of them. The name is at the bottom, so this is the KNN one.
Would this help you pick which would be better to use, the one that would
Yes.
affect the standard deviation at least?
Yes.
Okay, that makes sense.
Because that's one of the considerations, is that the variability can change. It can get wider or it can get artificially more narrow. And so if you pick something that generally is as close to the original of the rest of the data as possible. We can also plot these things. So one way to look at the data is always visually. So I'm going to create some histograms. And you can see where the mean and the median kind of popped up in our histogram because the bars are like huge. And you can see, like, again, the density curves, they pop up where those imputed values have we've added 100 values that have the same observation value. And so they are showing up very distinctly as peaks in our distribution. Again, this tends to be why the multiple regression or the KNN or some other regression method is better, because it doesn't put all of the values in one place. It kind of spreads them out a little bit more. So that was our histogram. And then if we calculate the variances for each of our situations, again, variance versus standard deviation, same basic idea. In the original age category, we had 142 variants. The closest one is actually the mode that did the least difference, but we saw that was stacked up in one particular place. So maybe the KNN is the one that is next closest in terms of the variance, but it doesn't affect the shape of the distribution as much. And then we can also do things like comparing the unimputed data to the target variable and see how that affects things like the correlation or the regression line. Because ultimately, like in this data set, we're trying to predict blood pressure. And we don't want to mess up the relationship between the input variables and the regression variable too much. So here I'm first just defining the target vector as blood pressure. And then again, we'll talk more about this when we do the modeling, but we're basically splitting this into test and training sets so that we can have an analysis of how good our model is, the imputed versus the unimputed data. And then we're going to, again, based on our model, calculate how good the model does relative to the relationship between our age variable, the original versus imputed, to our blood pressure variable. And the MSE is essentially like the standard variance, like the residual variance. It's not averaged exactly the same way, but it's more or less like that. And again, so you can see that for the age mean imputation, that is probably close to the median and the KNN imputation in terms of being similar to each other. But the one that had the least error was actually the regression imputation. So that one is affecting our ability, essentially producing the best ability to predict blood pressure. Now, we would want to be careful when we're doing this, because we would want to make sure that we weren't imputing the age from blood pressure when we did this step before. Here, when we were doing this imputation, it was not in our list. So again, we want to avoid those circular logic things where we use blood pressure to predict the missing age values, and then we use the age values to predict blood pressure. That's cheating. So you want to just make sure when you're doing this, this regression imputer, that you're not using the target variable to do the imputations. and we didn't, so we're good. So the fact that that model error is as small as it is in this case is a good sign that that may be a good way to do that imputation. Okay, so then we want to compare, these are the comparing the different imputation methods. We now want to compare with the original variable and see how we did just with the original 896 age components. And so if you see this, again, mean square error, it was 213 with the best imputed version, and without it, it's 204. So that is also an indication that we are making the least change to the power of our model by still keeping those observations, but we haven't made the mean square error that much bigger relative to what it would be if we just dumped the data. Now that's only based on dumping the 104 observations, not all the other observations that are also missing in the other categories, but normally you do these analyses one variable at a time before you build your model with everything else. And so we want to look at our a plot basically of our regression model, just so we can see how all of this looks again visually. So this is a quite long thing because it's basically doing all the steps that we've done kind of all at once. So we've written a function here to again put everything in one spot because we're going to do this for several different variables. So we just write it one time and then we just tell it, do it to this variable, do it to this variable. So we're splitting the data, we're doing our test and train split, we're fitting our regression model, and then we're going to plot a scatter plot and a histogram for the residuals. And then we're going to apply that to each of our imputed cases. And then also, I think down at the end, the unimputed circumstance. And again, this same process is going to be applied to each of our imputed variables. So we're going to get a lot of graphs here. And we'll sort of scroll through them. So the red is like our sort of default. The actual prediction for blood pressure is on the horizontal or the vertical axis, and the original blood pressure observations are on the vertical axis, or the predicted on the vertical and original on the horizontal. So the straight line indicates that the match would be perfect. And this is for, I believe, the mean. Yes, this is for the mean. So you can see that sort of what it did is it kind of spread the data out. So it's not on very close to the line really at all. That's our residual model. It looks normally distributed. It doesn't look too terrible. This is for the median. And so again, we have something that looks very similar. Again, histogram, this would put everything in the middle, so it doesn't look normally not, terrible. This, I believe, is the mode. Now this looks a little more skewed because the peak is further to the left. And so there is a longer tail. So this is not as good according to, it's not as normal, which is bad for our regression model. This is for KNN. And this one doesn't look too bad in terms of, again, the shape of our residual values. And then this is for the regression version, the regression imputation. And again, that one doesn't, shape-wise, doesn't look bad. It's not skewed. This is the actual age variable. And those residuals look pretty terrible. So this is left skewed now, which is different than our mode one, which became right skewed. So that would definitely suggest to me that we definitely did not want to use the mode imputation, because that was skewing the data in the entire opposite direction. It might also suggest that maybe our data is not missing at random. Maybe we're missing lots of young people from the state. I don't know why that would mean people wouldn't report their age, but this suggests there's not a lot of young people in this data set. And so most of our methods to impute the variables might have been, I mean, I don't know, but they might have been in giving us ages that were a little too old. It's hard to tell, but that would be something that I would be concerned about. And we can create a column to just indicate whether or not the age has been imputed. When we create our scatter plots, we might want to label on our graph, has this variable been imputed or not? Just so we can see how they line up on our scatter plot. And so that's what this is going to do. If we go scroll down to the end here, it's just creating a column of trues or falses. If there's a value there, it's false because it's not imputed. And if it says true, then it was missing before. And so we can use this column as a category label to change the color on our graphs. So we can visually see these were the values we imputed and these were the normal ones. And so here we're going to make a regression plot with a scatter plot and look at blood pressure versus the original age variable. This is with everything missing. And so it's not plotting anything that was imputed because it can't plot things that are missing. So this is just all normal. But if I impute with the mean, that red line of observations is where all my means are, which looks very artificial. And we can do the same for each of the other imputation versions. So again, the median does the same thing. It lines everything up in one spot at just a very slightly different value. The mode, all in one spot, but this is further over to the right. This is sort of part of a problem because you can see like these larger values above the regression line. This is going to pull that regression line up because these are relative to our regression line more extreme because they're further from the regression line. And it's going to have more impact on the results because it's further to the end and not in the middle. The least impact on the overall regression line will be if the outlier is in the middle of the graph, and it will have more impact when it's further out on the edges because it has more power for that slope, like with the torque, right? You don't put the door handle on the inside of the door, you put it on the outside of the door. Same thing. Now, if we impute with this is the KNN imputer. One of the reasons some of these regression imputers are preferred is because they do spread the data out, not all the way, but they do a better job spreading it out and not having it all bunch up in one spot. So this looks more normal, more natural. And then the regression one will look somewhat similar.
So,
but this one does produce more outliers in this case. Sure.
Sorry, but so why does it have the original imputed and then regression line on the legend? Why are there two of the like?
I think the colors are actually not, the labels are not quite right.
Okay.
Because the imputed is the dots in red.
Okay, yeah,
And the regression line is actually in gray.
right, okay, so let's just,
It's a labeling thing.
okay.
Yeah.
My second question was, if you were to take this data and say publish it, but you use the regression line to determine what those points should be that you imputed, but then wouldn't that feed into your statistical analysis?
Well,
later
remember,
on?
we use the regression analysis for the other independent variables, not blood pressure.
Oh, okay,
So we're not regressing on blood pressure.
okay,
This line across here is the regression between age and blood pressure,
Right.
but the red dots were not derived from blood pressure. That's why we
Gotcha,
went back
right.
to double check.
okay.
Those are
Oh, okay.
imputed based on income and smoking and exercise and alcohol intake.
Okay. That makes sense.
Now that would be harder to do if you had multiple observations that were missing on multiple lines, because you wouldn't necessarily have every variable available for every other variable. Whereas in this case, there's only one observation missing per line. So you can do the imputations on all the other variables because they always will only be missing the one thing. And so all the other variables will be there.
Okay.
The MBA data set we had would be harder to work with because there are multiple things missing on the lines that have missing data. So we'd have to be super, super careful about how we set that up. And then, of course, if you prefer numbers to pictures, you can calculate the correlations between the various age variables and the imputed and the blood pressure. So without any imputation, the correlation was 0.678. The mean correlation and the median correlation went down to 0.64. The mode went down to 0.62. That's that example that we were saying there's more variability. The regression and the KNN imputations went well, the KNN went down slightly. The regression one went up very slightly, but it's still, I mean, it's like instead of 0.678, it's 0.683. So, I mean, it's a very small change, but it technically went up. But that's the closest, it's in the same ballpark, which again, further suggests that this might be the best way to go. You don't want to artificially inflate the correlation. You also don't want to artificially deflate it either. So I've included a way to check for duplicates in here. Now you can check for duplicates for the entire data set. It's basically going to look at every row and make sure that it's not like any other row. Sometimes you have to clean the data that way because you'll get data from multiple sources and there will be replications and things like that. You can also calculate duplicates based on just one or two columns, or any subset of columns that you want. You need to be more careful with that because this says there are no duplicates overall, but there are 14 rows that have the same age and income. Now that could potentially be problematic, except that if you're doing something like values that don't have a lot of different outcomes, like maybe age and number of children, you would, especially in a large data set, you'd expect duplications. The fact that age and income are being duplicated, is that duplications in age only and income only? I would expect duplications in age. Or is this 14 rows that have the same age and income? Then I would worry. Because income is usually so many outcomes that you would, unless they're rounded, you would not expect the income to be the same to the dollar for anybody.
So maybe there's something wrong with your.
Right. So then you would want to investigate those further. Don't just delete them because they're duplicated, because especially if they're exactly duplicated, that's one thing. But if they're just duplicated on one or two columns, then you would not want to do that. Here, what we're looking at is we're pulling out the duplicated rows so that we can actually see if they are in fact duplicated. And it could just be that the income is what's missing, and that's why it's duplicated, because the age is the same. So if you have two 45-year-olds that are both have missing income, then that would register as a duplication.
I don't understand the output from this though, because you have like the 605, I'm guessing this individual 605 who's 33. I only see one other 33 one here, and they have a way different income than with that other one did.
Yeah.
So I don't understand why those are duplicates. Does it not print the other duplicate or just one duplicate?
It might be duplicated with something else further down on the list.
Oh, it only shows the first couple of rows?
So like for example, 791, row 791 has 56 in NAN, and 986 also has 56 in NAN. And as I said before, it might be pulling out, like, are there duplicates in the ages but not the income? Because I wouldn't expect the income to be duplicated, but again, this would be something they would be looking for in the mode calculations. And so again, you pull these out and then you want to do some inspections to see like what exactly is happening here. Yeah. And then there's a function for dropping duplicates. So once you're clear that you want to actually do this, you can either based on duplications from the whole data set or based on the duplications that you identified with just these two columns, you can specify dropping the duplicates. Again, it's a cleaning thing. We want to talk a little bit about working with data frames. So we're going to create a fake data frame and then we're going to do some stuff with it. One of the cleaning things that you might have to worry about is renaming columns in your data set, for example. So here I have a data frame. My original columns are just called ABC. And maybe I want to rename them as alpha, beta, gamma. Or again, whatever I want to name them as. I'm changing the name. So I would specify the rename function, and then I would basically have a dictionary. So I have the value I want to change and the value I want to change it to separated by a colon. And these are all text strings, so they're all in quotes. I can also, if I'm renaming all of the columns, I don't have to list which column I'm renaming. I can just list the names of the new columns.
It'll just go in the order.
Yes. Again, it's a typing thing. We don't want to type more than what we have to type. All right, so I'm reloading the practice data, and we're going to look a little bit at some SQL commands. So I'm going to load SQLite 3, and there's this connect option. Now, we don't have this data frame that I just loaded from the practice data in an actual SQL database, so I'm just loading it from memory. And then I'm going to convert this case. I'm just going to count all the indexes and see how big my table is. And it has 1,000 observations in it. So that's the number that's output here. So we can now, because it's loaded into a sort of memory SQLite database, we can now run SQLite commands on it. And what we're going to do is we're going to look at a little bit of a comparison between the way you would do this in Pandas and the way you would do this in SQL. So in this first one, we're going to pull out 2 columns from our table. So just age and gender. And then just look at the head of that for the first 5 rows. Now, if I want to do basically the same thing in SQL, I'm going to use my select function. I'm going to specify the column names that I want, age, comma, gender, from what did I call my table? Well, up here, I called it data to table. And then limit 5 is that head function. And I get exactly the same 2 columns with the same output. Now this thing here where I'm doing pd.readSQL query, that is specifying that it's going to convert it to a pandas data frame, because otherwise the default output for SQLite is text, which is a horrible way to work with data in Python. So we're going to convert it to a data frame so we can use it. All right, so now we want to do a filter. So again, in pandas, we would put in the brackets, we would specify here amount spent to be greater than 30, let's say. And so it's now like acting like a where function. Again, here's our actual SQL command, select star. So all of the columns from our data2 table where, again, in quotation marks, amount spent is greater than 30. And then this gives us, again, the head. I didn't put the limit function on there. I'll just do the head to look at it. But that pulls out all of that same exact data. And then I'm going to do group by. So this is our group by function in SQL. But in pandas, we also have a group by function. We're going to group by gender, and we're going to calculate the mean salary. So now we have a little table of salary by gender. This is obviously fake data.
But I like it.
I wish. And then in SQL, again, select gender, comma, average salary. And then we're renaming it as mean salary because we don't want the function as our header. And then from data2 table, and then we're grouping by the gender column. And so when we run that, we get exactly the same table. So a little bit of SQL, a little bit of imputation analysis, some general cleaning, more tools in our toolkit.
I like it.
Good. Now, next week, what we'll do, and I think this is the lecture I was writing this weekend, so I hope it's what I'm remembering. We're going to do more with SQL. We're going to do some cleaning of a data set, and then we're going to load that data into a SQL database. And we're going to do some queries on that new database. And we're going to bring in a much more messy school schedule database. And we're going to do some queries on that and some joins and stuff like that. So we'll get to practice this more as we lead up to project 2, which is our database project.
And that's over spring break, right?
That's over spring break. You'll have 2 weeks for that.
And you'll be here, right?
I will be around. Hey, my other jobs are still running.